Okay class, welcome to lecture 3 where we'll be discussing the law of total probability and the crucial concept of independence. Let's first start with an exercise related to countably infinite coin tosses to get us thinking. Consider a sequence of coin tosses. The sample space omega is the set of all infinite sequences of h and t. So omega equals ht raised to the n. For each n, let En be the event that the nth toss is ahead. So En is the set of outcomes omega in omega such that omega n equals h. Now consider an event space script f, which is the sigma algebra generated by the set of all such events, En for n in n. Let script fn be the sigma algebra generated by the first n of these events, Ei for I in 1 to n. Let an be the event that there is at least one head in the first n tosses. So an is the union from I equals 1 to n of ei. Clearly an is in script f, is in let bn be the event that the first head occurs on the nth toss. This means the first n minus 1 tosses were tails and the nth toss was a head. So Bn is the intersection from I equals 1 to n minus 1 of Ei complement intersected with En. This Bn is also in script f. Now for the exercise, first show that script f, the sigma algebra generated by all En, is equal to the sigma algebra generated by the collection of all script fn for n in n. Second, show that the sigma algebra generated by the sequence an for n in n is a subset of script f, and similarly the sigma algebra generated by the sequence bn for n in n is also a subset of script f. Now let's move to the law of total probability. Here's the theorem. For a given probability space omega script fp, consider a sequence of events b1, b2 and so on in script f to the n that forms a partition of the sample space omega. This means two things. First, bm intersect bn is the empty set for all m not equal to n. They are mutually disjoint. And second, the union over n in n of bn equals omega. They cover the entire sample space. Then for any event a in script f, we have the probability of ap of a is equal to the sum over n in n of the probability of a intersect bn. Let's look at the proof of the law of total probability. First, we can write the event a as a intersect omega. Since omega is the union of the bn's, we can substitute that in a equals a intersect the union over n in n of bn. Using the distributive property, this becomes the union over n in n of a intersect bn. Now consider the sequence of events a intersect bn for n in n. Since the original bn sequence is mutually disjoint, this new sequence a intersect bn must also be mutually disjoint. Each of these a intersect bn events is in script f. The result then follows directly from the sigma additivity axiom of probability applied to the sequence of disjoint events. P of A, which is P of the union of A intersect Bn, equals the sum of P of A intersect Bn. Let's consider an example related to our countably infinite coin tosses. The sample space is omega equals ht to the n, and the event space script f is generated by the sequence E, where En is head-on nth toss. We observe that any event A in the smaller sigma algebra script Fn generated by the outcomes of the first n tosses can be written as the union over all elementary outcomes omega in A of the set containing just that omega, each such elementary outcome omega, which is a sequence of h and t of length n, followed by anything, can be expressed as an intersection of events ei or ei complement. That is, A equals the union for omega in A of the intersection from I equals 1 to n of either the event omega is in EI or the event omega is not in EI. Now let's define independence of events. For a probability space, omega script f P, a family of events, A in script f to the I, where I some index set is said to be independent if for any finite subset f of I, we have the probability of the intersection over I in f of AI, P of intersection AI is equal to the product over I in f of P of AI. A quick reminder, the certain event omega and the impossible event empty set are always independent of every other event A in script f. You can check this using the definition. Let's look at an example with two coin tosses. The sample space omega is HH, HT, TH, TT, and the event space script f is the power set of omega. Let's define the probability P such that P of HH equals P of H, T equals P of TH equals P of T, T equals 1 by 4. This is a fair coin assumption. Let event E1 be HHHT, which corresponds to getting ahead on the first toss. Let event E2 be HHTH, corresponding to getting ahead on the second toss. The probability of E1, P of E1 is 1 by 2, and similarly P of E2 is 1 by 2. The intersection event E1 intersect E2 is the set HH, and its probability P of E1 intersect E2 is 1 by 4. We can see that P of E1 intersect E2, which is 1 by 4, is indeed equal to P of E1 times P of E2, which is 1 by 2 times 1 by 2. Therefore, the events E1 and E2 are independent. Let's extend this to countably infinite coin tosses. The outcome space is omega equals HT to the n, and the event space script f is generated by the sequence E, where En is head on nth toss. Let's define a probability measure P from script f to the closed interval from 0 to 1, such that for any finite subset f of n, P of the intersection for I in f of E, I equals P raised to the power of the cardinality of f, where P is the probability of a head on a single toss. Under this definition, the sequence of events E, E1, E2, and so on is a sequence of independent events. Now consider An as the union from I equals 1 to n of EI, at least one head in first n tosses, and Bn as the intersection from I equals 1 to n minus 1 of E. I complement intersected with En first head on nth toss. Both are in script f. The probability of A and P of An works out to be 1 minus P to the n. And P of Bn is P times 1 minus P to the n minus 1 for n in n. For any outcome omega in omega, let's define Kn of omega as the sum from I equals 1 to n of the indicator of H for omega I. This is just the number of heads in the first n tosses for outcome omega, which is also the sum from I equals 1 to n of the indicator that omega is in EI. Then for any event A in script Fn, the sigma algebra generated by the first n tosses E1 to En, we can write P of A as the sum for omega in A of the product from I equals 1 to n of P if omega is in EI, or 1 minus P if omega is in EI complement. This is equivalent to the sum for omega in A of P raised to Kn of omega times 1 minus P raised to n minus Kn of omega. It's important to be careful with the definition of independence for more than two events. Consider a probability space omega script F, P and three events A1, A2, A3 in script F.
Just having P of A1 intersect A2 intersect A3 equal to P of A1 times P of A2 times P of A3 is not sufficient to guarantee the independence of these three events.
In particular, if P of A1 intersect A2 intersect A3 equals P of A1 times P of A2 times P of A3, but P of A1 intersect A2 intersect A3 complement does not equal P of A1 times P of A2 times P of A3 complement, then P of A1 intersect A2, which is P of A1 intersect A2 intersect A3 plus P of A1 intersect A2 intersect A3 complement will not be equal to P of A1 times P of A2. So A1 and A2 would not be independent, meaning the collection is not independent. The definition requires the product rule to hold for all finite subcollections. We can also define independence for a family of collections of events. A family of collections of events, script AI, which is a subset of script F. For AI in an index set, I is called independent if for any finite subset F of I, and for any choice of AI from script A, I for all I in F, we have P of the intersection for I in F of AI equals the product for A in F of P of AI. Now let's move on to conditional probability. Consider n trials of a random experiment with outcome space omega and event space script F. Let omega n in omega denote the outcome of the nth trial. Let A and B be two events in script F. We can count n of A, n of B, and n of A intersect B as the number of occurrences of these events in n trials. So n of A is the sum from n equals 1 to n of the indicator that omega n is in A. Similarly, for n of B and n of A intersect B is the sum from n equals 1 to n of the indicator that omega n is in A intersect B. From these counts, the relative frequencies of events A, B, and A intersect B in n trials are n of A over n of B over n, and n of A intersect B over n respectively. Now, if we want to find the relative frequency of event A specifically on those trials where event B also occurred, we would calculate this as n of A intersect b over n divided by n of b over n. This simplifies to n of A intersect B divided by n of B. This motivates the definition of conditional probability. Fix an event B in script F such that its probability P of B is greater than 0. We can define the conditional probability of any event A in script F given the event B, denoted P of A given B as P of A intersect B divided by P of B. We have a lemma stating that this conditional probability is itself a valid probability measure for any event B in script F with P of B greater than 0, the function P of dot given B mapping from script F to the closed interval from 0 to 1 is a probability measure on the space omega script F. Let's prove this lemma. First, non-negativity for all events A in script F, P of A given B must be greater than or equal to 0 since P of A intersect B is greater than or equal to 0 as P is a probability measure and P of B is positive. Second, sigma additivity for an infinite sequence of mutually disjoint events, I in script F for I in N with AI intersect AJ being empty for I not equal to J, we need to show that P of the union over I in N of AI given B equals the sum over I in N of P of AI given B. This follows because the sequence AI intersect B for I in N is also a sequence of mutually disjoint events. Third, certainty. Since omega intersect B equals B, P of omega given B equals P of B divided by P of B, which is 1. Thus, conditional probability satisfies all the axioms. Here are some reminders about conditional probability. For two independent events A and B in script F such that P of A intersect B is greater than 0, which implies P of A is greater than 0 and P of B is greater than 0. We have P of A given B equals P of A and P of B given A equals P of B. If either P of A is 0 or P of B is 0, then P of A intersect B is 0 due to independence or monotonicity. Also, for any partition B, B1, B2, so on of the sample space omega, if P of Bn is greater than 0 for all n in N, then from the law of total probability and the definition of conditional probability, we can rewrite the law of total probability as P of A equals the sum over N in N of P of A given Bn times P of Bn. Now let's define conditional independence of events. For a probability space omega script F, P, a family of events, A in script F to the I is said to be conditionally independent given an event C in script F where P of C is greater than 0 if for any finite subset F of I we have P of the intersection for I in F of AI given C equals the product for I in F of P of AI given C. Some reminders on conditional independence. Let C be an event in script F such that P of C is greater than 0. Two events A and B in script F are said to be conditionally independent given event C if P of A intersect B given C equals P of A given C times P of B given C. If the conditioning event C is the entire sample space, omega and P of omega equals 1, which is greater than 0, then this definition reduces to A and B being simply independent events. It's important to realize that two events may be independent but not conditionally independent and vice versa. Let's look at an example illustrating this. Consider two independent events A and B in script F such that P of A intersect B is greater than 0 and P of A union B is less than 1. Are A and B conditionally independent given the event A union B? Let's check. P of A intersect B given A union B equals P of A intersect B divided by P of A union B. Since A and B are independent, this is P of A times P of B divided by P of A union B. Now, P of A given A union B is P of A divided by P of A union B. And P of B given A union B is P of B divided by P of A union B. For conditional independence, we would need P of A times P of B by P of A union B to equal P of A given P of A union B times P of B given P of A union B, which simplifies to needing P of A union B equals 1. But we are given P of A union B is lesser than 1. So they are not conditionally independent. For instance, P of B given A union B is P of B divided by P of A union B, which is generally not equal to P of B. Therefore, P of A intersect B given A union B will not equal P of A given A union B times P of B given A union B. Now consider two non-independent events A and B in script F such that P of A is greater than 0. Are A and B conditionally independent given A? Let's check. P of A intersect B given A is P of A intersect B intersect A divided by P of A, which simplifies to P of A intersect B divided by P of A. On the other hand, P of B given A times P of A given A is P of A intersect B by P of A times P of A intersect A by P of A, which is P of A intersect B by P of A times 1. So yes, they are conditionally independent given A. This might seem trivial, but it illustrates the definition. This concludes our lecture on the law of total probability and the concepts of independence and conditional independence.